On August 9, 2026, high above the mountains of Chile, a machine quietly opened its eye to the night sky. There were no crowds gathered around it, no dramatic countdown, and no breaking news sirens. Just darkness stretching across the Andes and a telescope patiently taking photographs of the southern sky. Every few nights, it would return to the same patches of space and take another picture, then another, and another. To most people, those images would look almost identical. Before we go any further, if you enjoy stories about space, unexplained discoveries, and the mysteries hiding beyond our planet, take a second to subscribe to the channel and help us reach 1,000 subscribers. But the machine wasn't looking for things that stayed still. It was looking for anything that moved, anything that flickered, anything that suddenly appeared, and anything that had never been there before. The machine was the Vera C. Rubin Observatory, and in the months surrounding its first operations, it had already begun uncovering something astonishing. More than 11,000 objects in our solar system that human beings had never known existed. Not 11, not 1,100, 11,000. Among them were 33 near-Earth objects, rocks whose paths cross or approach the region of space occupied by Earth's orbit. Objects that, until this year, nobody had been tracking. And then there were hundreds more hiding much farther away. Beyond Neptune, in the frozen darkness at the outer edge of the solar system, Rubin had begun finding hundreds of trans-Neptunian objects. These weren't simply pieces of rock drifting through space. They were ancient leftovers from the birth of our solar system, frozen for roughly 4.5 billion years. They were fossils, frozen pieces of a time so distant that Earth itself looked completely different. And every one of them had a story to tell. But while Rubin was quietly mapping the darkness around our sun, another telescope was looking in a completely different direction. Far away from Chile, the James Webb Space Telescope was turning its attention toward one of the most recognizable worlds in the solar system, Saturn. For decades, astronomers had watched Saturn and noticed something that refused to make sense. The planet seemed to have a broken clock. Its apparent rotation rate appeared to change. Not dramatically, not enough for anyone to watch Saturn and see it suddenly spinning faster or slower, but enough for scientific instruments to repeatedly produce different measurements. Mission after mission, instrument after instrument, decade after decade, the numbers kept shifting. It was almost as if Saturn itself were speeding up and slowing down. But that shouldn't happen. Saturn is enormous, with roughly 95 times the mass of Earth. A planet that massive doesn't simply change its rotation rate for no reason. And so, for more than 4 decades, the mystery remained. It wasn't the kind of mystery that dominated headlines every morning. It was something quieter. A persistent inconsistency buried inside the measurements, quietly frustrating planetary scientists for generations. Then, in 2026, the James Webb Space Telescope looked at Saturn with a level of precision previous instruments simply couldn't match. And the mystery began to unravel. The answer was not that Saturn's actual spin was changing. The planet had never been behaving like some cosmic dial after all. Instead, something much higher above the planet had been fooling scientists. Saturn's auroras. Just like Earth's northern lights, Saturn produces enormous auroral displays around its poles. But on Saturn, these lights are connected to a much larger system. The auroras heat the planet's upper atmosphere. That heating produces powerful high-altitude winds. Those winds generate electrical currents, and those electrical currents feed back into the auroral system, creating a self-sustaining loop unfolding continuously above Saturn's cloud tops. For decades, Scientists had been measuring the effects of this moving, changing system and interpreting them as clues about the planet's rotation. The planet wasn't changing its spin. The atmosphere around it was changing. And now, for the first time, astronomers could begin separating the two. But to understand why that discovery matters, you have to understand the machine that was watching the rest of the solar system. The Vera C. Rubin Observatory sits more than 2,600 meters above sea level in the Chilean Andes. Its camera is unlike anything astronomers had ever built before. It is the largest digital camera ever constructed for astronomy, roughly the size of a small car and weighing around 3,000 kilograms. Its images are so enormous that displaying a single one at full resolution would require hundreds of ultra-high-definition televisions lined up together. And yet, despite its enormous size, Rubin's basic idea is surprisingly simple. Take a picture of the sky, then come back later and take the same picture again. Then do it again, and again, and again. If something has moved between those images, Rubin notices. If something suddenly becomes brighter, Rubin notices. If something disappears, Rubin notices. And if something appears where nothing existed before, Rubin notices that too. Astronomers call the project the Legacy Survey of Space and Time, or LSST. The plan is to photograph the visible sky repeatedly over the next 10 years. Imagine a security camera pointed not at a street, but at the universe itself. That is essentially what Rubin is doing. And the first glimpse of what this machine could accomplish came on February 24th, when engineers conducted a major test of its alert system. The telescope looked at a single patch of sky, one patch, and in one night it generated approximately 800,000 alerts, 800,000 changes. Objects that had moved, appeared, disappeared, or otherwise behaved differently from the previous observations. And somehow, all of that information was distributed to astronomers around the world within roughly 2 minutes. But that was only a test. The real survey would be far larger. Once operating at full capacity, Rubin is expected to produce up to 7 million alerts every night, along with roughly 20 terabytes of new data. And then it will do it again the following night, and the night after that, for 10 years. The scale is almost impossible to comprehend, but even before the full science mission had formally begun, the observatory was already producing results. During roughly the first month and a half of early survey operations, Rubin had identified more than 11,000 asteroids that had never been seen before. Among them were the 33 near-Earth objects and hundreds of objects beyond Neptune. And that number becomes even more astonishing when you compare it with the history of astronomy itself. For roughly 200 years, human astronomers gradually built a catalog containing around 1 million asteroids. 2 centuries of observations, generations of astronomers, and countless telescopes. And now, one machine is expected to discover another 1 million asteroids in just its first year. 1 year compared with 2 centuries of human discovery. And suddenly, Rubin begins to look less like an ordinary telescope and more like a machine for rewriting the map of our solar system. Every night, it searches through the darkness for something we haven't seen before. A new asteroid, a forgotten comet, an object moving through the outer solar system, something approaching Earth's neighborhood. Or perhaps something so strange that astronomers don't even know what category to put it in. And that's what makes the timing so extraordinary. Because while Rubin is casting its enormous net across the sky, James Webb is doing almost the exact opposite. Rubin searches widely. Webb looks deeply. Rubin finds the things nobody knew were there. Webb can then focus on individual targets and study them in extraordinary detail. One telescope watches almost everything. The other can stare intensely at one thing. And together, they are beginning to give astronomers something humanity has never had at this scale before, a way to discover the unknown and then immediately begin investigating it. For the first time, the solar system isn't simply being observed. It is being continuously mapped, monitored, and revisited. And somewhere inside that growing mountain of data, there may already be objects waiting to change what we think we know about the world surrounding our sun. Because Rubin has only just begun. One machine, 1 year, matching 2 centuries of human discovery. And suddenly, the question changes. When people ask what Rubin is actually for, the honest answer is simple. It's the most powerful solar system discovery machine ever built. Right now, it is in the process of redrawing the map of everything orbiting our sun. Comets we've never tracked. Asteroids on collision courses we didn't know about. And perhaps most importantly, objects far out near Saturn, Uranus, and Neptune that have spent billions of years sitting in the darkness, completely invisible to us until now. And this is where it gets personal. Imagine standing outside on a clear night, looking up at Saturn through a small backyard telescope. You can see its rings, even from millions of kilometers away. And for a moment, you realize that you're looking at another world. But what if everything you can see is only a tiny fraction of what's actually out there? Because Rubin isn't finished. In fact, it's only beginning. Scientists are already calling the next major data release, expected between July and September of this year, a major milestone. Every one of the trans-Neptunian objects Rubin has discovered carries information about the ancient history of our solar system. Billions of years ago, Saturn, Jupiter, Uranus, and Neptune weren't necessarily sitting exactly where we see them today. As the giant planets moved through the young solar system, their enormous gravity disturbed and rearranged the vast disk of icy debris surrounding the sun. The objects Rubin is finding now are remnants of that ancient process. Each one is essentially a fossil, a frozen clue preserved for billions of years, carrying evidence of how the giant planets moved and how the architecture of our solar system was created. And while Rubin has been sweeping across the sky, searching for these ancient objects, another telescope has been doing something completely different. The James Webb Space Telescope has been staring directly at one of those giant planets, Saturn. And what Webb discovered has helped solve a puzzle that had been frustrating scientists for decades. For decades, going all the way back to the 1980s, when NASA's Voyager spacecraft first flew past Saturn, astronomers had noticed something strange. Saturn's rotation rate seemed to change. Not by much, but enough to matter. Different spacecraft, different instruments, and different observations kept producing slightly different numbers. It was almost as though the entire planet were speeding up and slowing down like some enormous cosmic dial. But that shouldn't happen. If someone tells you that a planet the size of Saturn is randomly changing its spin, your first reaction should probably be skepticism. Saturn has roughly 95 times the mass of Earth. A world that massive doesn't simply decide to spin a little faster one day and a little slower another day without some enormous physical force acting on it. And yet, for more than 40 years, the measurements continued to produce this strange inconsistency. It wasn't a mystery that dominated every newspaper or appeared on television every night. It was something much quieter, but perhaps even more frustrating to the scientists studying it. A nagging inconsistency that refused to disappear. Every new observation seemed to get researchers closer to an answer, only for another measurement to raise the same question again. Was Saturn's rotation actually changing, or were scientists measuring something else entirely? Then came 2026, and the James Webb Space Telescope entered the story. With its extraordinary sensitivity and ability to study Saturn's atmosphere in infrared wavelengths, Webb gave researchers a much clearer look at what was happening above the planet's clouds. And finally, the mystery began to crack. The answer was not that Saturn's spin was changing at all. The planet itself had been behaving normally. The problem was that something in its atmosphere had been confusing the measurements. Saturn's northern auroras, yes, Saturn has auroras just like Earth's northern lights, except vastly larger and stranger, were actively heating the planet's upper atmosphere. That heating created powerful high-altitude winds. Those winds generated electrical currents, and those electrical currents then looped back into the auroral system, helping power the aurora again. The result was a self-sustaining cycle continuously operating high above Saturn's cloud tops. For decades, scientists had been measuring the effects of this constantly changing atmospheric system and interpreting some of those signals as clues about Saturn's actual rotation. But the planet wasn't speeding up or slowing down. Instead, a shifting, self-reinforcing system of auroras, winds, and electrical currents was moving above the planet and throwing off the measurements. Saturn's clock wasn't broken. Scientists had simply been watching the wrong clock. And here's the part that should genuinely impress you. To understand what was really happening above Saturn, the researchers needed something previous missions had never been able to provide: an extremely precise measurement of temperatures and charged particle densities in the planet's auroral region. Earlier missions had produced measurements with uncertainties of roughly 50 degrees Celsius. That might sound remarkably precise at first, but when you're trying to detect subtle changes happening across a vast planetary atmosphere, that level of uncertainty is like trying to understand the temperature of a room while wearing thick gloves. The details simply disappear. Webb changed that. Its observations were roughly 10 times more precise, allowing scientists to see localized patterns of heating and cooling across Saturn's atmosphere, instead of being forced to rely on one blurry average. The researchers accomplished this by tracking a specific molecule that naturally forms in Saturn's upper atmosphere. That molecule produces a glow that changes with the conditions around it, effectively turning it into a built-in thermometer. By carefully mapping how that glow changed from one region to another, the team was able to construct the most detailed temperature and particle density maps of Saturn's auroral region ever produced. Suddenly, the invisible processes happening high above Saturn's clouds were no longer just theoretical. Scientists could actually see their signatures in the data. And when you strip away all the technical language, the discovery becomes surprisingly simple. A mystery that had followed scientists for roughly 40 years, involving a planet more than 90 times the mass of Earth, had finally been explained. Saturn's actual spin wasn't behaving strangely at all. The real problem was that astronomers had finally found a way to separate the planet itself from the constantly changing atmospheric system riding above it. The planet wasn't the thing changing. The weather system was. That kind of discovery might not always dominate the front page, but its importance reaches far beyond Saturn. It changes the way scientists think about the atmospheres, auroras, winds, and magnetic environments of gas giants in general, including worlds that humanity hasn't even sent spacecraft to yet. And Webb wasn't finished with Saturn. Earlier in 2026, NASA released a remarkable set of combined observations using both the James Webb Space Telescope and the Hubble Space Telescope. Two of humanity's most powerful observatories were looking at exactly the same planet, at essentially the same time, but through completely different types of light. Hubble sees Saturn in visible light, the same general range of light that human eyes can naturally detect. Through that view, scientists can study subtle color variations across Saturn's atmospheric bands, storms, and cloud structures. Webb, however, sees Saturn primarily through infrared wavelengths, allowing it to probe deeper and detect clouds and chemical signatures at different altitudes, from the deep, turbulent lower atmosphere all the way up to the thin, wispy layers near the edge of space. Scientists have compared using the two telescopes together to slicing through an onion. Each layer reveals something different. One wavelength shows you one part of the planet, while another wavelength exposes something hidden underneath. When the observations are combined, Saturn becomes more than just a beautiful sphere surrounded by rings. It becomes a layered, constantly changing world whose atmosphere can be studied from multiple depths at once. In Webb's infrared images, Saturn's rings can appear almost blindingly bright. That's because they're primarily made of highly reflective water ice, and infrared light interacts with that ice differently from visible light. The contrast allows researchers to see details that can be much harder to distinguish in ordinary images. Some structural features in the rings appear differently depending on which telescope is observing them, including subtle, spoke-like structures in the B ring and the incredibly thin, crisp appearance of Saturn's outer F ring in Webb's data, details that barely stand out in Hubble's visible light observations. And this wasn't simply a single observation made for a dramatic photograph. The Hubble image included in the combined release came from a much longer monitoring program that has been following Saturn's atmosphere for more than a decade. Scientists have been watching the planet's face, clouds, storms, and rings slowly change as Saturn moves through its own enormous seasonal cycle. And Saturn's seasons are nothing like ours. Earth completes an orbit around the Sun in 1 year, but Saturn takes roughly 29 Earth years to make a single trip. That means a season on Saturn can last for years rather than months. The planet changes slowly enough that a human lifetime captures only part of one complete Saturnian cycle. Put all of these discoveries together, and the picture becomes much larger than any single telescope or single mystery. Here we are on August 9, 2026, watching one observatory quietly catalog tens of thousands of solar system objects that were previously completely unknown to humanity. At the same time, another observatory, or more accurately, two of them working together, is revealing details about Saturn that are helping solve mysteries that have challenged planetary scientists for decades. One machine is expanding the map of our solar system. The others are teaching us how to read the worlds already on that map. And neither story is finished yet. And the strangest part is that neither of these stories needed any fake urgency to make them interesting. There was no 3 minutes ago, no mysterious object suddenly appearing out of nowhere, and no manufactured breaking news drama. There were simply real telescopes doing exactly what they were built to do, observing the universe with extraordinary precision and uncovering results that were already far stranger and more fascinating than most exaggerated headlines could ever make them sound.